So colleagues, I have been given the honor of introducing the speaker today, who is our own Professor Franco Sevilla. He is an experimental particle physicist, came here in 2018. Before that, he did his undergraduate in Spain, in Madrid. And then he came to the US to do graduate work at Stanford, where he joined the Kovar experiment, which at the time was focused on studying CP violation, matter, antimatter symmetry, and a standard model. But then they decided that he and his colleagues decided that they'd look at something else, which was to see how leptons are produced in the decays of the B mesons. B mesons are mesons which contain the B quark. And they found something quite surprising. And their result, which indicates, and it's still a valid result at the level of about 4 sigma, indicates that there is larger number of tau leptons, the heavier leptons produced than the other leptons. And that violates one of the cornerstones of the standard model known as Lepton Flavor Universality. Manuel, this was done in 2012. This made Manuel quite famous, which then decided that he moved on to something else. He moved to the CMS experiment to directly look for CP for the new physics, and he didn't find any. In 2018, he joined Lepton, and he joined the LHCb experiment, which looks at the B quarks again. He immediately took a leadership role in trying to design and build the next generation of the LHCb detector, and continued to look at Lepton Flavor Universality. So that's part of the story, and I'm happy to invite him to tell us the rest of the story.
Okay, can you hear me? Yes, perfect. Thank you very much, Hassan, for that very kind introduction. Let's see if I can put this back. And yes, indeed, I'm going to be talking about new physics, perhaps, in heavy flavor, in heavy quark decays. And the whole title, I understand, is a mouthful, but I'll promise I'll try to explain each step in detail. And so the overall outline of the talk, I will start actually defining what new physics is and the main strategies to try to find it, the machines that we use in this endeavor. I'll then actually define what Lepton Flavor Universality is and those famous hints of possible violation. And I will end with a very visual story of how we build this next generation of silicon tracker for LHCb and what we can expect for Lepton Flavor Universality with this upgraded detector. So first, let me get you back to the end of the 19th century. As you know, after the what? So as you know, after the scientific revolution, our understanding of gravity, electromagnetism, and thermodynamics exploded to such precision that some people at the end of the 19th century, including the first American Nobel Prize winner, Albert Michelson, had the feeling that physics was done, that all the grand underlying principles of physics had already been established. We could only then find more decimals to the parameters of the theories that we knew. Of course, not everyone thought that way, and even Lord Kelvin, in his address to the Royal Society in 1901, said that yes, this is a beautiful and clear picture, but it's a present obscured by 2 clouds, and that would be the ultraviolet catastrophe and the negative result of the Michelson-Morley experiment. We all know now that these 2 little clouds would gather strength and would usher in the era of modern physics. First, with the beginning of quantum physics and special relativity, which very quickly gave rise to the best description of gravity that we have found to date. And then through more development in the 20th century, eventually it all culminated with the standard model of particle physics in the 70s. This beautiful theory that just tells you that with a quantum field theory that satisfies this SU3, SU2, U1 symmetry in just a few fundamental fields, you have the most comprehensive and precise theory of mankind, something that can make predictions of 10 digits in this anomalous magnetic moment of the electron that have been experimentally confirmed. And so since then, we've had further experimental confirmation of these 2 beautiful theories, more recently gravitational waves and the discovery of the Higgs boson, but no new theoretical framework that describes the universe at its most fundamental level. So you may as well wonder, like they wondered at the end of the 19th century, is physics done? Is there anything else left to discover? Or are the clouds in front of this beautiful picture? And the answer is a resounding yes. Why is the rotational velocity of galaxies following this curve as opposed to this one? Or why, when you do gravitational lensing in the bullet cluster, you see gravitational mass in the blue stuff, but there's no standard model particle that is in the blue place. So that's what we call dark matter. Or in the standard model, matter and antimatter are basically treated pretty much the same. If you have a neutral boson like this and you generate matter, like an electron or muon, you always generate antimatter with it, the positron and antimuon. So why is you basically should be generating equal amounts of both? When you look into the universe, you don't see anti-galaxies or anti-Manuelis giving anti-colloquia. So we don't know. And there's other more technical questions, like why is the expansion of the universe accelerating, or why these two beautiful theories don't seem to share a common framework. And so there's a lot of clouds out there telling us that these two theories is not the explanation of it all, that there has to be some new physics, a new theoretical framework that may be capable of explaining some of these clouds. And so within particle physics, the main strategies that we follow to look for new physics are direct searches and indirect searches. And so direct searches is what it sounds like. You directly produce the new physics. In particle physics, the new particle, and detect it. And this is what we did for the Higgs boson, where we collided protons hard enough and frequently enough that we generated enough Higgs bosons that when you plot them in something like this, you see a little peak at 125 GeV that tells you, hey, there's a new particle. In this case, it was not new physics, because this particle is squarely within the standard model, but this is how you find new physics. And this is how I spent years of my postdoc, along with many others, searching, for instance, for supersymmetric particles, like these two gluinos, or these two neutralinos that would be a good dark matter candidate. However, myself and everyone else at the LHC ended up with plots that look like this, exclusion plots. So this is a plot that tells you that, as far as you can tell, this decay doesn't occur for gluinos of less than 2 TeV and neutralinos of less than 1 TeV. So this whole thing is excluded. And basically, when you directly search for new physics at the LHC, this is what we've been finding so far. And this is why so much of the energy has shifted towards indirect searches, in which you actually do precision standard model measurements. Then you compare them to predictions within the standard model, and you may be able to detect virtual contributions to those standard model processes. And these virtual contributions may be at a higher energy than what the LHC can produce directly. This is the power of indirect searches. And this was actually something that was crucial for the development of the standard model. And for instance, in the 60s, we looked at these neutral kaons. This is the neutral kaon, and this is the anti-kaon. And so these are the so-called flavor eigenstates, but just like the neutrinos, they're different from the mass eigenstates, so they can oscillate into one another. And actually, by studying these oscillations and the decays of these kaons, which are just half a GeV, we were able, before we had the energy to produce charm quarks, we were able to predict that this loop actually had an additional quark there that was 3 times heavier than the charm quark. And also, because there were some differences between matter and antimatter in some of these decays and these oscillations, we knew that this was not enough. These 2 quarks don't give you CP violation. If you want CP violation, you need a 3rd generation of quarks. In this case, the top quark there, which is way heavier than what we could do in the 60s. And so you can see how these indirect searches can lead the way to new physics beyond the energy scales that you can directly produce. So that's what we do at LHCb. Measurements that give us access to mass scales beyond the reach of the current particle accelerators. Before I continue, let me define a piece of terminology. So you probably all know that there's 6 types of quarks, right? D, U, S, C, B, and T. Half of them charge 2/3, half of them charge 1/3. But which charge? That's the electric charge. There's other charges, like the color charge. So actually, you could say there's even more types than this. There's like blue quarks, green quarks, and red quarks. So there's like another dimension, another type that we call color. And so there's many different types, right? So just to have the nomenclature clear, we use the nomenclature that Murray Gell-Mann and his student, back when they went to a Baskin-Robbins in Pasadena, they said, we can have ice cream that is red with different flavors. So, it's the same thing as quarks. You can have many red quarks, but they come with different flavors. And so this is why myself, Professor Hamilton, and Professor Jahir, we are all flavor physicists. And I'll be talking about flavor physics, which is the study of the different kinds of quarks and leptons. All right, so that was the introduction. Let me tell you about the machines with which we measure these physics. And so all flavor physics has to start with the flavor factories, the B factories, these two beautiful experiments that operated at the beginning of the 21st century, colliding positrons and electrons, one in California and another one in Japan, which have been more recently joined by Bell 2, the super B factory that will be taking data until 2035. The advantage of these kind of colliders is that you collide fundamental particles. And so you end up with often just a pair of B mesons and nothing else. And so the events look as beautiful as this. Okay, this is a three-dimensional rendering. They really look like this, but still very, very clean. And so if you know that your initial transverse momentum is 0, you can almost by eye say, hey, this missing transverse momentum here. And like with these machines, you can actually measure that there was a neutrino, 1.2 GeV neutrino there with very high precision. And so I will contrast these experiments with the Large Hadron Collider, which, as the name says, we don't collide fundamental particles, we collide protons, and they are a messy mix of quarks and gluons. And we have in these rings 4 major experiments, ATLAS and CMS, the largest, with the largest coverage. So those are the best ones to discover new physics, and that's why they also discover the Higgs bosons. And then we have LHCb, which focuses on precision flavor measurements, and as I said, basically indirect searches for new physics. And then there's also ALICE, which does a very different kind of physics, heavy ion, that I will not describe in this talk. I'll be focusing on LHCb, which is a collaboration that has grown immensely. We are now over 1,800 members, and of the 105 institutes, 8 are now American. And the detector looks like this. The protons collide here, and so you can see that basically all the particles that we'll be measuring are in the forward direction. ATLAS and CMS cover this area here and here, the central region. We focus on the forward, and the reason we focus on the forward is this plot, which tells you the BB bar production as a function of the pseudo-rapidity, the angle. So this is the central region that ATLAS CMS measures. And we focus on this forward region with just covering 4% of the solid angle. We actually cover 25% of all the BB bar that is produced. And that's why we care about Bs. And how do we measure this? In case you don't know particle detectors, they have many layers like this. Neutral particles are like ghosts that just go through all the layers without doing much until they hit the calorimeters. Photons, the electromagnetic calorimeter, and hadrons, the hadronic calorimeter. These neutral particles are very hard at LHCb, and we typically focus on the charged particles. Particles that leave charge in the trackers. So we have 3 trackers, and so you can see here the track nicely followed with the 3 trackers. You can also see the bend, which comes from the magnet, and this bend allows you to measure the momentum of these tracks. This is why we like them so much. And then a big advantage of LHCb over CMS and ATLAS is our ability to differentiate charged hadrons, protons, kaons, and pions, thanks to these Cherenkov detectors here. And then, of course, we have muon detectors. If you see a charged particle that is capable of going through the steel that we have in the muon stations, you know it is a muon. Okay, so what can we do with this detector? Well, a lot. But the environment is quite hard. It doesn't look like the B factories at all. I mean, it looks like this. It's a real mess. And so really, to make sense of this, you need this key thing here. The fact that the B meson's lifetime, it's super long, 10 to the minus 12 seconds, like orders of magnitude longer than the other particles. But that seems short. But with the large energies at LHCb, and thanks also to the relativistic boost, they can fly centimeters before they decay. And so basically, we have this vertex locator here, and that can measure the decay of the particles there. Like if you zoom in, you see this is our beautiful vertex locator, lots of hits, and it can tell here, for instance, you can see that we have 6 muons because they got to the muon stations here. Are all of them interesting? Well, we can see which ones come from the primary interaction and which ones not. And so if you zoom in here, you see that 2 of those 6 actually come from the secondary vertex, not the primary interaction with the protons colliding. And so you have these 2 muons here. It means that there was a neutral particle that flew from here to here and then decayed into the 2 muons. If you do the invariant mass of the two muons, you see that it peaks at the mass of the B sub s meson, so you know, oh, I had a B sub s meson there. And so these vertex capabilities are basically unique and what sets LHCb apart together with the particle identification capabilities. And to highlight LHCb's capability, I always like to show the B sub s, an oscillation very similar to the K-on oscillation that we can measure in hadron colliders. So basically this is the flavor eigenstates again oscillating to one another. You can measure it even in LHCb where you collide protons and you generate B and B bar by tagging this guy here that we call flavor tagging. And so if you have a B bar here, you know you had a B here. And so you know the B sub s was an anti-B sub s. And then this anti-B sub s may oscillate into the B sub s, and then it may decay into something like this, and the charts of this spine tells you that it actually had oscillated and decayed as a B sub s. And so that tells you that basically you started with like this, and you oscillated like this. And then for those of you who may have taken quantum mechanics with me and remember second order perturbation theory, you can actually calculate this oscillation probability with a B sub s mixing, and it gives you a probability something like this, the hyperbolic cosine and a rapid oscillation, a cosine, with the difference in mass eigenstate masses and the time. So if you're able to measure the time, you can measure this oscillation of one into another. And in LHCb, you can measure this time very well because it's just proportional to the distance between these vertices, given that it flies the speed of light. And so actually the first guys to measure this were Professor Belloni and their friends at Tevatron, at CDF. This beautiful oscillation here is this cosine, where you did modulo 2 pi over delta m to add up all the oscillations here. Well, with a few more years and the vertex precision, the tagging precision, and the increased BB bar cross-section of LHCb, this plot has now become the most beautiful plot. So look at this. You can see basically all the oscillations, and each oscillation has incredible precision. You can see quantum mechanics with your own eyes. And so this is basically a plot that really shows you the capabilities of LHCb, but of course this is with all charged tracks in the final state. What I'll be describing now is not all charged tracks in the final states, because there's these freaking neutrinos here that nobody sees, except those neutrino people, but they don't see all of them either. So what is first this Lepton Flavor Universality? Okay, so I've been telling you about the standard model. And the standard model has these fermions here, 6 of them are leptons, and they are neatly separated into 3 generations. If you look at the gauge bosons, they interact with all of these guys. For instance, the Z boson can interact with 3 generations of leptons. The coupling of the interaction, how strongly they interact with each of the generations, it's given by a parameter GZ, which is identical for the 3 generations. That's the key assumption with the standard model, that the electroweak gauge couplings, this coupling here is the same for the 3 generations, not only for the Z boson, but also for the W and the photon. So for all electroweak bosons, these couplings are identical between the 3 generations, and the only reason why we can tell an electron and a muon apart is because they interact differently with the Higgs boson. There you have a coupling that is proportional to the mass. But other than that, they are identical. So that means if we measure an interaction that is different between these 3 generations, other than the difference induced by the different masses, we have tested the standard model and we have found new physics there. And so this is super interesting. And of course, we are not the first ones testing this. This has been tested for decades now. And so Lepton Flavor Universality has been proven to be true to very great precision between electrons and muons in Z decays, W decays, meson decays, and tau decays with very good precision, and also between 3rd generation taus and electrons, Z bosons, D sub s, and taus again. Of course, science is never a straight arrow. You always find some bumps and anomalies along the way, and there was a long-standing anomaly coming from LEP in W decays at 2.6 sigma tension, and even LHCb found this tension between K mu mu and K e of 3 sigma. But these 2 anomalies are now gone. Actually, Atlas measured this actually to be consistent with Lepton Flavor Universality and LHCb as well. So basically, Lepton Flavor Universality is not an assumption that we just made up. It's, as far as we can tell, it's really, really true. This is why it's so interesting that when you start looking at these decays here, B going to this symbol means that it's either a D or a D star meson, either of them. So a D or D star, tau, and nu. that we see something that may deviate from Lepton Flavor Universality. And that we do with these ratios here. So this is the ratio of how often this decay happens. This is the branching fraction. How often B decays to D or D star tau nu versus how often it decays to the light lepton. This curly L is either a muon or an electron, a light lepton. So we're going to measure these two ratios, RD and RD star. And the interesting thing here is that these are ratios that within the standard model framework you can predict to great accuracy, about 1 to 2% precision. And that's key because you're going to basically compare your measurement to a prediction, and you want the prediction to be as precise as possible. And so if you measure something that does not agree with these two numbers, then you found new physics. Basically, this is the standard physics. This decay should occur through a virtual W. But if the measurement doesn't agree with the prediction, it means that you have some additional virtual contributions. It could be a charged Higgs, or it could be an exotic leptoquark, or something else. So that's what we are going to do. This is really hard. And the reason why it's so hard is because you try to measure this decay. And so the D decays all to charged tracks is easy. You see the D. But the tau decays like this. It decays to a lepton that is easy and 2 neutrinos that are impossible. Those 3 neutrinos are undetectable. So the only particles that you see is the D or the D star and the light lepton. You not only have to measure this, our signal, you also need to measure the denominator of the ratio, which we call the normalization of the whole thing. And the denominator is just with the light lepton. The light lepton is stable. So basically the final particles that you see for the normalization and your signal are identical, exactly same visible particles. And this is great because then in the ratio, the efficiency for the D and the light lepton are going to cancel out. So these ratios experimentally are also pretty easy because all of these uncertainties cancel out. But the difficulty is that they have the same visible particles. So how do you separate a DNL versus a DNL? Because you don't see how many neutrinos you lost. And so that's the key thing where the B factories are so good. The B factories, what they do is they use this variable called missing mass, where you have the form momentum of the signal B, and you subtract the form momentum of the particles that you see, the D and the L. And so this basically is the invariant mass of everything that you're missing. And in this case, the 3 neutrinos. And in the case of the normalization, 1 neutrino. So if you have 1 neutrino, this basically is 0 within detector resolution. If you have 3 neutrinos, it's a broad resolution. And so this is how you're going to separate it. But for those eagle-eyed of you, you may say, hey, but you don't know what this is because you only reconstruct this guy and this guy. You don't know the momentum of these 3 guys. In the B factories, you actually know it because you collide electrons and positrons of which you know the momentum. They generate 2 Bs. If you generate the attack B, then you can calculate this momentum as just the initial momentum minus the attack B that gives you the signal B momentum. And this actually works really well. This is a plot from my thesis where you can see that the invariant mass of normalization events indeed is very sharp, a little bit less sharp when you miss the pion, but it's still very sharp compared to signal. Signal is in this tail here, very broad. We can zoom in into there and you can see the signal in green and in red. Very well separated from the normalization here, sitting on top of a smallish brown and yellow background over there. So what we found in my thesis was this measurement here. So this is the measurement of RD and RD star, the 2-dimensional measurement, and this is the 1 sigma ellipse for both measurements. And this is the predictions in the standard model. And so you can see there's some distance between them, which was about 3.4 sigma, which created big news. And since then, it has been a very interesting problem to try to solve. And so the other B factories have been trying to get the best measurements here, and they actually have 3 additional measurements. And this is why this is such an interesting measurement, that you end up with all of these end up being kind of above the standard model. And this is why it would be really interesting if LHCb also could add more ellipses here to really know whether these ellipses are significantly different from the predictions or not. But as I said, LHCb is really good with charged particles. Here we have 3 undetectable neutrinos. How can we do this? Many people thought we couldn't. But then Professor Jawahari and Hamilton came up with this idea. So in LHCb, we don't have this. We don't collide electron and positron. We don't have a B tag. We cannot calculate the signal B momentum like this. What we do instead is use the vertexing capabilities of LHCb. So you have a decay like this, and you can reconstruct this vertex and this vertex. That gives you the direction of the momentum of this B signal. And then in addition to knowing the direction, you can do a clever assumption of the proper velocity of the visible particles. And that doesn't give you a perfect reconstruction, but it's good enough. You can see that the missing mass of the normalization in LHCb peaks at 0 as it should. It just has a broader tail. The analysis is like this is way more complicated because this broader tail means that you're not separating so well the signal and the normalization. So they had to add more variables to the fit. One of the variables that they added is Q-squared, which I will not describe. But the key thing is that the most sensitive bin in Q-squared is the last one. And even if you look at the last one, the missing mass looks like this. So the signal is this sliver of red sitting on top of a huge background compared to the background that we had here. So not only you have to add more variables to the fit, you have to understand this huge background really well to be able to do this measurement. And to understand this background, basically you can come up with control samples. For instance, to understand this yellow background, you come up with a fake muon sample that has a lot of mis-ID background. To understand the purple background, which are D double stars that like to decay into 1 pion or 2 pions plus a charm meson, you can add that pion to 2 pions to understand that purple background well. And the same thing for the double charm in gray, you add an additional KN. So there was a lot of work crafting these dedicated control samples and understanding them. There was a preliminary measurement of RD star in 2015, but the full measurement of RD and RD star took a decade to be ready. And that looks now like this. So here we have the B factories, and you have a competitive measurement by LHCb that is still, again, it's a little bit above the standard model. In addition to these are the most precise measurements, but this is such an interesting problem that there have been other less precise, powerful measurements. All the measurements so far look like this. And so if you do the experimental average, you get this red ellipse, which is now 3.8 sigma away from the standard model. And this is why this is one of the most interesting problems in particle physics today. And so this is why we are very excited that we are coming really, really close to having an update with the run 2 data. That means 2 times more luminosity than the run 1 data that we use for this blue ellipse, 2 times higher BB bar cross-section, and up to 100 times higher efficiency, thanks to better trigger and better selection. That means up to 10 times more B mesons than their one result. And so we're still working on refining the background model. For instance, these double stars, we're adding new variables to try to disentangle them. It's pretty hard, but we really hope by next year to have this new result that if we are able to control systematics, will actually be perhaps the most precise measurement in the world. So the uncertainties that we expect is something like this ellipse here if you place them at the same central value as the run 1 result. And so if we keep doing this and finding results that keep being away from the standard model, we may end up finally with a 5 sigma observation. But that would be a really big deal. And as our friend Carl Sagan used to say, extraordinary claims require extraordinary evidence. I mean, even if we get to 5 sigma in these weird decays, we may not believe we have new physics. You would need something else, like a correlated pattern of anomalies, because these are, as I'm trying to impress, really hard measurements. Perhaps we're doing something wrong, even though we have like 3 different experiments doing complementary measurements. And so this is another place where LHCb plays a key role, because I've been focusing on RD and RD star, where you have this B to C tau nu transition, and this is spectator quark in green. You can change the spectator quark and keep the B to C tau nu transition like this, and then you have different ratios. So if you put an S quark, you have RD sub S. If you put a C quark, you have RJ psi. And if you put 2 quarks, you have a baryon, a lambda B going into lambda C. And so you can measure these other Lepton Flavor Universality ratios that are only accessible at LHCb. The other B factory cannot measure these 3 here. LHCb and CMS can also have some sensitivity to this. And so we already have preliminary results for RJ psi and R lambda C compared to the standard model here, and CMS also has 1 measurement for RJ psi. And so the problem here is that you can see that these ones are much harder, these 3, and you can see the uncertainties are very large. We have our own Emily trying to shrink those uncertainties, hopefully by next year. But we need a lot more data to have really precise measurements of this. And so this will be my segue to explain why we need a better detector so that we can measure these LFU ratios and also the kinematic distributions of these decays along with many other things. And so I'm going to explain for the last section of my talk this project where we built a new silicon tracker and what we can do with the upgraded LHCb. So the results that I've shown you so far, Lepton Flavor Universality, B sub s to mu mu, B sub s oscillation, and many others that I haven't had time to explain, like the exotic tetraquarks and pentaquarks that we found at LHCb, they're all based on what we call run 1 and run 2, the data taken until 2018. This data was taken with a trigger strategy like every other particle physics detector in a hadron collider. It has two stages, one based on hardware, meaning that you make trigger decisions based on ASICs or FPGAs, hardware. Like it's very difficult to change. You cannot make sophisticated algorithms there. But this is too large a rate to read. So you simply don't have the bandwidth or the ability to make decisions at 40 megahertz. So you need to reduce the 40 megahertz to 1 megahertz very quickly, even if it is dumb, so that then with computers, you can then do sophisticated algorithms to analyze these megahertz and get the interesting events out. So this is what we did in round 1 and 2, but this has a limitation. Our luminosity didn't grow very quickly because we had to defocus the beams. So our luminosity here was always way below the luminosity at less than CMS. Even if we increase the luminosity, we wouldn't get more data. So this is, as you increase the luminosity, you have to increase the trigger threshold in this dumb trigger. And as you increase the trigger threshold, your yield doesn't increase. It saturates for hadronic decays. And you don't want to lose the hadronic. So basically, this detector was not good enough to take data faster. So that's what we tried to fix. So that's what we did, the upgrade 1 during long shutdown 2, this time here, so that we can take data about 5 times faster than we did earlier on. And so this trigger became this beauty, the first hadron collider detector with no hardware trigger. The first hadron collider detector where you read the full 40 megahertz of data, select the most interesting events, and then write out to disk. And so to do this, we had to fully change the electronics, and we have this new trigger based on a first layer of GPUs and then CPUs, and then completely build from scratch the 3 trackers. And I'll be focusing on this middle tracker here, the upstream tracker, because this is where Maryland had key contributions. And so this upstream tracker, or UT for the friends, it's 4 layers of silicon strips. So you can see here the 4 layers, some of them straight, some of them tilted, so that you can basically find the X and Y. And they're crucial for triggering and for long-lived particles that may not decay in the velo. And so if the vertex is past the velo here, you need this UT to then measure those particles. These vertical structures here are called staves. And so you can see here the silicon sensors, they're on both sides of the staves. Silicon sensors are this mirror-like thing here that I'm zooming in. So the silicon sensor here, you have the ASICs that read it out, wire bonded to the silicon strips, then an electronic board called the hybrid, and then everything is read out on the flex cable. And institutions that collaborated to make this happen are shown here with 6 from the US, led by Syracuse and us. And so the readout of these sensors looks like this in a cartoon form. So you have the silicon sensor, the ASICs digitize it, and then you have the hybrid that sends the signals through the flex cable to this backplane and the data control boards. The flex cable and the backplane are connected via this pigtail flex cable, pigtail because it has this little curl, as you can see there. And then here you have the brain of the data acquisition, the DCBs that basically control the front end boards and then take all the data that comes from the silicon sensors and ship it out via fiber to the central DAC. So basically the readout chain looks like this, and Maryland's responsibility was these 2 boards, the backplane here and the DCB. But additionally, Maryland was responsible for the low voltage systems, these low voltage regulators that provide power not only to the DCBs, but also to the silicon, to the hybrids here. And this was a very sophisticated system where you may have some voltage drop in this cable. So you want to basically provide very precise voltages here, but you don't know what voltages you have here unless you add sensing. Sensing are these additional cables that carry no current, so they tell you what voltage you have here, and so what voltage you have to output here to get the right voltage here. And so these were the contributions from Maryland, the data control boards, radiation hard, provide radiation hard slow control, and the optical transmission with these chips here, the optical transceivers and the serializers, deserializers. Then you have the low voltage regulators that have these radiation hard chips designed by CERN, and everything is controlled by an FPGA. And then the backplane, which simply basically routes the data that is very concentrated on one corner into the 12 DCBs. It balances the load. So basically from here to all 12 DCBs. And so I always like to ask when I show this slide of these three boards, which one you think may have been the most challenging. But obviously, I mean, these ones are super sophisticated, so the most challenging must have been the backplane, which it was a nightmare. We really thought we wouldn't pull it off because you have this super high density of traces here that we needed 28 layers to take them out. 28 layers with connectors that had pins separated by 800 microns, so you could only put like 150 micron vias. And if you know anything about PCBs, if you have a thick PCB with a very narrow via, is basically unmanufacturable. And so this ratio that was 19, typically manufacturers say that cannot exceed 10. And so we had to find first engineers that were able to do this. We had one in Oregon that couldn't pull it off, and eventually another one at CERN was able to route it, and then a manufacturer that was able to do this. But yeah, after 4 or 5 years, we managed to design all these boards and validate the design. The key engineers were Tom O'Bannon, Larry Lutz, and our own Professor Hamilton, who moonlighted as an engineer over those years. And then we spent quite a bit of time validating these designs. Here we have 2 undergraduate students checking the design of the LVR. Here I'm testing the DCBs connected to this stave here with tests such as the eye test, where you test that the optical connection is stable enough that it has a big open eye, as you can see there. But after the design, the project had just beginning because there was a lot of assembly. All the mechanical components to get the heat out of these boards, the optical mezzanines, you have basically about more than 2,000 of these little screws to install to secure the optical transceivers. You need to check that the thermals are okay. Here's Professor Jauher measuring with an infrared camera that the DCB indeed is not toasting. Same thing for the LVR. A lot of mechanical assembly and checking that the thermals are good. And so we had to do this for like hundreds of boards and thousands of these little boards. And for that, we assembled this amazing army of 10 undergraduates that we trained at the beginning of 2020. But of course, you know what happened in 2020 after they were perfectly trained. We just lost them. That was very sad. And this was a really big blow because for 3 months, we had the lab closed. We could only do documentation, software, and firmware. Firmware, actually, that I could do in my apartment. I stole this oscilloscope and the power supply, the board, and then with the help of my piano stand and the bread maker box, I was able to write the firmware for the LVR. And then during the summer, we resumed the shifts, but initially only grad students, postdocs, and faculty. And then in September, we started having some undergraduates. In the end, we lost almost a year there, but we managed to assemble everything by 2021. Where before that, you have to make sure you detect any infant mortality. So we cycled these backplanes with 50 cycles of cold hot. The LVRs and DCBs, we just turned them on with maximum load for 2 days. Then we had to figure out a way to safely ship everything. But by April 2021, we reported that everything had been produced. And so that was what we had told NSF that we would do, producing these boards. But of course, these boards are useless if you don't have a detector that actually uses them. And we were very close to being in that position because the UT was just not ready at that moment. We had hoped to install all the infrastructure here, but things got delayed kind of until 2020, and then COVID hit. And because this was a very non-European, most of LHCb projects are European-centered, but this one had like all this contribution from the US. It was very hard to get senior leadership to CERN, get people. We had a student stuck in China for over half a year. So it was really, really tough during 2020. Slowly, we were able to manage to send people. And here we have one of our grad students requalifying the boards. We got set up with a clean room, a huge cabling effort. But by 2022, here you can see the project leader of the UT at the end of 2021 saying that history has its eyes on us because we really had to deliver. The whole LHCb collaboration was starting to think what would happen if basically there was no UT, and they could run, but they could not run nearly close to the design luminosity. So they really needed a UT. And so during 2022, we did do quite a bit of progress with cables, fibers for half, and the staves, we started assembling them slowly, one every week. But then in June, the coordinator had to leave CERN. And so that's where it wasn't super easy for me, but I was the option to take care of this, and so they elevated me to deputy project leader, and more importantly, to the installation coordinator for the whole effort at CERN. And so basically I got there in July, and the first thing was basically getting this stave installation quicker than one stave a week. And so this stave installation has many steps, but the most difficult is the convoy, because it requires 4 people. So you need, for this 30 minutes, 4 people 7 days a week. So you need to make sure that you have 4 people trained to basically bring this 1-pound stave, so this is me on a bunny suit, to the detector, and then you basically need 4 people, because there's 3 plus the spotter, to very carefully put the stave there. And then there's other steps, like the high voltage. You connect the high voltage cables, you shine a light to detect whether they're well connected via the dark current that you get with the light. The pigtails that were a little bit difficult to plug on the backside, so there's like this mirror to see the backside, and the last step was these CO2 pipes for the cooling that also were a little bit tricky. But in the end, optimizing this, we managed to do 3 staves a day, which was enough to assemble the whole thing in the last 6 months of the year. But those 6 months had a lot of emotions there. There was also the other half of the infrastructure that took months earlier on. We had to do in about 4 weeks for the fibers and the low voltage. Here you see a microscope checking that the fiber is clean. One of my favorite problems was measuring where this cutout was. This cutout is the cutout in the middle of the detector that allows the beam pipe that carries the protons in the LHC to go through the detector. So obviously you design it not to hit the beam pipe, but if you install it in the wrong place and you hit the beam pipe, the whole LHC crashes. And so you want to double check that this is where you think it is, but the designers of the silicon sensors would not allow us to touch the stave. But here I had to do a bit of an executive decision, because what I understood that is that they didn't allow us to touch the silicon sensor. The stave, if we managed to touch the stave only, it was fine. So we designed this contraption here to touch just in between the silicon sensors on both. And so this allows us to put a reflector there that then you survey, and you can measure with micrometer precision where this cutout is. So at the end of the day, on Saturday, December 10th, we managed to finish the 2 halves like that. And so then the next step is like to push it out of the clean room very gently, and then you put it on a truck, and then you go 5 kilometers an hour through CERN, everyone filming, because there's millions of dollars and hopes and dreams in a little box. So you hope it makes it all the way to the cavern. And then you take it to the cavern, you bring it down the 100-meter shaft down to the LHCb cavern where it spent the night. And half of this detector has to go over the LHCb detector that is here. And so here we are hoisting it and passing it to the other side to install it there. And then by the end of 22, we managed to have both halves installed here, and you can see the beam pipe going right through the middle. And so this was the hardest stuff, the hardest part of the job, but there was still a lot of work left. There's a lot of cables that you have to put in, and here we had to defy the European custom of taking the whole Christmas break. And so CERN always closes for 2 weeks, but we had to convince them to bring a bunch of volunteers to work through those 2 weeks to continue cabling this until March 2023. But this part was a lot easier, and we could even celebrate New Year's together, and I finally could escape to the Alps to do some climbing, so we were very happy with that. And so this project now, after 1 hard year of commissioning, it's working really well. So remember, the UT is here, and it's critical, for instance, for particles that fly for a little bit and decay after the velo, like this one. And so this kind of particle, lambda going to proton pion, now we can reconstruct beautifully. And if you look at the whole LHCb, just in last year, 2024, we took more data than the holes runs 1 and 2 combined. And when I showed this plot back in June at a conference in Cincinnati, the Bell 2 physics coordinator said that this plot where LHCb goes vertical gives him cold sweats at night, because we're kind of in competition with them, but not really. I mean, we are all scientists. We just want to find the truth. We are complementary to Bell 2. But this is pretty remarkable how fast we are taking data now. But not just we're taking data fast, we're efficient. since we removed the level 0 trigger, we went from this efficiency at low momentum to this efficiency here. So we're way more efficient at low momentum than before. And because our whole trigger is done in GPUs and CPUs, you can put really sophisticated, for instance, machine learning algorithms. For instance, like this Lipschitz constrained neural network that reconstructs dimuons. You can see the beautiful dimuon spectrum, all the particles. You can see this little blip here, that's eta to mu mu. Thanks to this algorithm, we are now 20 times more efficient for these low momentum muons. So for those theorists who care about dark sector decays, like something with low momentum muons, LHCb is now your detector. So it's working really, really well. And this is why we believe we have a great case to keep improving our detector. And we were just approved to fully exploit the high luminosity LHC by doing a second upgrade. That is a little enhancement that is coming up in long shutdown 3 and a big upgrade in long shutdown 4. And I'm really excited about this because Maryland is now gearing up to contributing again to do a critical contribution, this time to the PicoCal, which is an electromagnetic calorimeter with femtosecond timing resolution. And so far, Professor Hamilton and Jauhari are leading our efforts, but as the UT is winding down, I really hope to start contributing here. And for those undergraduates among you not in the last year, in about 1 academic year, we expect to be recruiting undergraduates for this project here, so pay attention. But the question is, what can we do with this amount of data? And basically with that amount of data, so remember, all the results that I showed you use 9, we are going to have 300 more. The uncertainty on RD and RD star would come down like this. This is at the end of run 2, we will have a 5% uncertainty. We could go down perhaps to 1% if systematics are low. So we really would be able to get to 5 sigma in RD, RD star for sure. But the key is not 5 sigma only here, it would be also basically with the other ratios. And when I say 5 sigma, I just mean uncertainties that are small enough if you stay at the current central values, you get to 5 sigma. Of course, we may find that is completely compatible with standard model. But so with this amount of data, you get to about 5% in these other Lepton Flavor Universality ratios. And then something that I'm really excited about is you would also be able to measure kinematic distributions. For instance, in my thesis, I measured the Q-square distribution for D star tau nu and D tau nu. And you can see that, for instance, already with that amount of data, I was able to say that the new physics that I kind of saw with Babar, it was not a pure scalar. It was not just a pure charge Higgs. It agreed much better with standard model, which is a mixture of scalar and vector. But there was a bit of an excess here and decrease here. And actually, if there was any new physics, that data already hinted that it would be probably more like a pure vector. And this is something that so far we don't have enough data to do at the LHCb, but with these big data samples, we hope to be able to do it. So in summary, I hope I convinced you that the LHCb detector is working really, really well. And it's very interesting because these measurements that people didn't think we would be able to do, RD and RD star, we've recently been able to publish a very competitive measurement, and we hope to have an update soon that may have really good uncertainties. And these, as I said, are very interesting because there's some hints, perhaps, of new physics. But the future is really bright. We are very excited because we have now upgrade 1 to exploit, which is working really well, and now we have upgrade 2 to build. And so for the foreseeable future, we expect to be having fun with this. And if you're an undergraduate student, welcome to join. Thank you, and any questions?
We have time for questions, plenty of time.
So are there beyond standard model theories that make predictions about ratios and exclude, or there's an infinite number of them?
There's an infinite number of them. Yeah, so for a long time, we thought, I mean, the reason why we started looking at this was charge Higgs. We were going to find supersymmetry in the LHC. It was going to be coming with these charge Higgses, and this was a mode that was very sensitive to charge Higgses. But of course, then we found something interesting, but the interesting was not compatible with charge Higgs whatsoever. So basically this was kind of excluded, at least the charge Higgs, the most basic charge Higgs. And so the one that was until recently really, really popular was a very specific type of leptoquark, especially when we had these other anomalies in RK. There was like this beautiful pattern of anomalies like, oh man, we have it. But the other ones went away. Here, now you still have some leptoquarks that work well, but there's many things that you can fit there. And so as usual, I'm an experimentalist. I mean, I'm going to go with the data take us. It may take us to the standard model, or it may take us somewhere, but like if you measure these distributions and these ratios, I think we will eventually know exactly what it is.
Thanks, Manuel, for congratulations on this remarkable effort and outcome. So I guess my question is, how much confidence is on the standard model predictions are ratios? I know to some extent, but I want to know your opinion.
Yeah, no, so, I mean, the sense, my feeling is that if either of them were to be, there would be a problem either in the experimental side or on the theoretical side. It would be in the experimental side, which is extremely challenging. On the theory side, the nice thing is that you're doing ratios. And so the ratios are easy experimentally, but also very easy theoretically. And so basically, there's not much that could go wrong here, especially because so far, so I said we have 1 to 2% uncertainty there, even if it was like 4%. The effect that we see right now is like 15%. So if we can do a small uncertainty on that 15% separation, I mean, you would have new physics. So this is why it's so important that the experiment really gets there. I'm sure the theory will be no problem.
Is there any other measurement for the tau? Because this is, maybe related to tau, left tau, or something straight. But there are other instances you have tau electrons coming out, right? Not just in the BFIT, but there are also other kind of processes with taus.
You talked about
Yep.
Z and
So there's many LFU tests with taus. And there was actually, people were very interested because when I came out with this result, there was this big anomaly in W going to tau nu versus W going to mu nu, that there was also an enhancement there. This has since gone. And so there's many measurements with the tau we don't see there. This is a little bit why the prejudice is that eventually these anomalies will go away. Because it's very, very strange. I mean, like, why is it only affecting the B mesons and you don't see it in Z decays, in W decays? We don't have an answer for that. The only thing that I can say is I'm an experimentalist. I'm going to measure the heck out of this and see where it takes me.
B measure without the tau doesn't have any problems there. Like,
Say that again?
the B meson decay without the tau will not have any problems.
You mean muon versus electron?
Yes,
Yeah, muon versus electron. This is another test that they are doing more often these days, but as far as we can tell, muon versus electron is the same in the B meson, in the B decays. The thinking was, like initially when we were looking for charge Higgses would be proportional to the mass of the lepton. So if there were a charge Higgs, you would see it much earlier on the taus than on the light leptons, because the effect would be proportional to the mass. Now that we don't think it's a charge Higgs, it could still be something that's proportional to the mass that you only see on the tau sector. So that would be easy. But anyway, we don't know. I mean, you don't see it in these taus here, so.
Any other questions? I don't see any other hands up. Let's thank this